Hello and welcome back to Calculus. First, I'd like to thank all the nice people that support this channel by liking and subscribing. It really helps a lot for me to grow and continue making math videos for you guys. In the previous video, we looked at the construction of the tangent and normal of a curve. Today, we will explore another application of derivatives, precisely finding the maximum and minimum points of a curve. I'd like to begin this by visualizing what happens when we try searching for these maximums and minimums. Given a function f, you can clearly see that our curve has two different points, the maximum point on top and the minimum point on the bottom. These points can also be called the turning points of a curve. This is because looking at the behavior of a function, here the function rises on top, reaches the maximum point, and then starts to fall down. Subsequently, as it's falling down, it comes to the minimum point and then starts to grow. Basically, the maximum and minimum show when our function changes direction. These points also have another name called the stationary points. They are called stationary points because when we look at the tangent of the curve at these maximum and minimum points, we can see that it's just a straight horizontal line. Basically, y equals to some number a. This means there is no gradient, or to be more precise, the gradient is equal to 0. And this fact here is basically how you compute the maximum and minimum points of a curve. If you have a function f of x and they asked you to find the stationary points or the maximum and minimum, your first step would be to evaluate the derivative of f and then equate it to 0. Once you have calculated, you would get one x value or sometimes maybe even 2. And these x values would correspond to the x value of your stationary points, basically the x coordinate. And of course, when you plug in the x values back into the original f of x function, what you get are the corresponding y coordinates. And then these 2 points would be the stationary points of a curve. However, though we have identified the stationary points, how do we classify whether it is a maximum or a minimum? Well, step number 1 would be to draw a number line. And then you would put the 2 or several or maybe just one x value you got from equating the derivative to 0. Now in our case, we have 3 intervals from -infinity to x1, x1 to x2, and from x2 to positive infinity. And then we would pick one random number from each of these 3 intervals. Let's say they are a, b, and c. The next step would be to plug in the a, b, and c into our derivative. And here comes the property of derivatives. It simply means we're searching for the gradient at that specific point a. Naturally, a can be any number from the interval -infinity to x1. And if we get a value greater than 0, that means our function is increasing because this gradient or the slope is positive. If we get the value less than 0, that means our function starts to decrease because a negative gradient suggests that the function is decreasing. Let's say we do this and we get greater than 0, less than 0, and greater than 0 again. We would then go back onto the number line and put the plus signs for the positive gradient and negative signs for the negative gradient. From this information on the number line, it tells us that from this interval -infinity to x1, our function was increasing, and then it reached a point x1 and started decreasing. Logically, that would mean that x1 is a maximum point. And of course, from the interval x1 to x2, we got a negative gradient, suggesting that our function is decreasing until it reached the point x2, and then the function started increasing again from the interval x2 to positive infinity. And this suggests that x2 is a minimum point of the curve. What's drawn here on the number line is basically the same thing as the green and red arrows on the original f curve. If this is still a little bit confusing, let's go ahead and take a look at an example. We are given the function 2x to the power 4 minus 4x squared plus 1, and we're tasked with finding the maximum and minimum points of this curve. By theory, step number 1 would be to find the derivative. With the power rule, we get 8x cubed minus 8x, and then we equate the derivative to 0 and solve for x. I factored out 8x, and I have x squared minus 1 left in the parentheses, so an obvious answer is x equals to 0. However, there are two more. Precisely, x squared minus 1 has to equal to 0, thus meaning x squared has to equal positive 1, and x can be equal to plus minus 1. So here we have received three different x values. So let's put them first on the number line. Now we have four different intervals, and we need to pick a random number from each interval and put them into the derivative. For the sake of simplicity, let's say I pick -2, -1/2, +1/2, and +2. Here I receive the following values. So this basically tells us that we have two plus signs and two minus signs. Again, from a minus turning into a plus suggests that -1 is just a minimum point. And of course, from a positive sign to a negative sign suggests that 0 is a maximum, and subsequently 1 is also a minimum. So now that we have identified the stationary points and also classified them as maximum and minimums, all we need are their y-coordinates. And we can simply do this by plugging in these three roots into the original 2x to the power 4 minus 4x squared plus 1 function. And finally, I get 3 points, -1 and -1, which is a minimum, 0 and 1, which is a maximum, and 1 and -1, which is a minimum again. Indeed, it isn't so complicated. Just don't mix things up. For the number line test, you plug your arbitrary chosen numbers into the derivative function. And then for the final answer, when searching for the y-coordinates of your stationary points, you plug in the x values into the original f of x, or the original function. However, once again, this seems a little time-wasting. If the derivative had only one or two roots, then this number line test would still be okay. However, in our case, our derivative function, when equated to 0, had three different roots, and testing all different numbers, the calculation already became quite lengthy. Thus, in the next video, I will show you a trick that could make it much easier. It has something to do with the function's second derivative, and also what kind of points come from it. And that's right, you heard it correctly. The second derivative does indeed exist, and even more, the third and the fourth, and so on. So I hope to see you in the next video, and have a nice day. Bye.